viewers, in this session I will discuss on the various methods of map overlay, auto-spatial correlation and network models. Map overlay: integrating two or more different thematic map layers of the same geographic area is a common operation in GIS analysis. The technique of map overlay has many applications, such as visual comparison by overlaying a map showing only hospitals on a road network map to answer the query that where are the hospitals located. In this case, no new data set are produced. This technique is also used for overlay of vector data on a raster background image, which is a scanned topographic map. Vector overlay: in a vector based system, the analysis is based on polygon intersection algorithm, in which new polygons are created as needed and redundant boundaries are eliminated. Vector map overlay relies heavily on two associated disciplines of geometry and topology. The data layers being overlaid need to be topologically correct boundaries, so that lines meeting at nodes and polygon boundaries are closed. To create topology of a new data layer produced as a result of the overlay process, the intersection of lines and polygons from the input layers need to be calculated using the required geometry. In this particular slide, what we find is that a vector map showing different classes of residences adjoining a business area. This can be classified as class A residences, class B residences and the business center. However, what we can do is we can generalize the information and we can merge class A, class B residences and say this is residential area, and on redefining the features, the net result is that we will now get a bigger area, which will now have a feature classification of residential area, which is general, which does not typify what category or class of residences are located and where they are located. It just shows the residential areas and the commercial areas, that is commercial area is the business area has been redesignated as a commercial area. So, this is what we call it as merging and redefining of features. Vector overlay. Vector overlay, there are three main types of vector overlays. These are point in polygon, line in polygon and polygon on polygon. So, let us look at each of these one by one. Point in polygon: when it is desired to locate a point with respect to polygons, that is in which polygon a point lies, point in polygon overlay is used. The figure in the next slide shows two data layers containing wells as points and soil types as polygons. The point in polygon overlay on these layers result an output layer indicating that in which soil category the wells lie. This information is given as an output map of a new set of wells created with additional attributes describing the soil type. So, here what we can see is that there are three types of, there are three wells and they have been located as a point. We have the soil map, which is a polygon map, and it shows two categories of soil, sand and clay. And when we undertake this overlay process of point in polygon, it tells me that well number 1 and 2 are located within sandy soils, whereas well number 3 is located within clay type of soil. So, having done this operation, we will now have a attribute table information, wherein there would be two types of information. One would be the well ID and the second is the soil type associated with it. And thus, it would appear well number 1, soil is sand, well number 2, soil is sand, well number 3, soil is clay. And thus, now the analyst is in a better position to understand which type of soil is present in each type of well which has been located in a given area. The next type is line in polygon. To answer the queries whether a road lies on sandy or clay type of soil, line in polygon overlay is used. The figure shown in the next slide shows data layers of roads and soil types. When the two layers are integrated, the roads are split into smaller segments, depending on which part of a road falls in which type of soil category. A database record for each new road segment is created in the output map. The output layer is more complicated than the two input layers, as topological information is required to be retained, and therefore, line in polygon is more complex. So, here we see two types of maps. One is a line map showing the roads which are there, a polygon map which shows the different types of soils which are there, and when we apply the point in polygon the line in polygon overlay, we get a line map wherein now the road has been split into much more smaller segments. Earlier there were 3 segments which were there, that is 2 individual segments and the combined part. But now what has happened is that there has been a further subdivision of the individual links or segments of the road. And so, what we find is that the first segment of the road, which was there were only 3 segments, now the first segment has been broken up into 2 segments. Similarly, the second segment in the original layer has been again broken up into 2 segments. So, what we are now going to have is a new line attribute table, wherein we will have the old ID of the road, the new ID of the road and the soil type. So, what we find is that the old road which has now been split into 2 segments 1 and 2. So, we will have 2 new IDs 1 and 2, wherein the first segment of the road is falling over soil type, the second segment of the road is falling over K type. Similarly, the second road in the input map again has been broken up into 2 portions, and thus it will now have 2 new ID, one segment having ID as 3, and this falls over sandy soil, while ID 4 falls over clay. Since after the intersection of these 2 roads, it is only one single road which is proceeding, and this particular segment is over a single soil layer, and thus the third road, which has now been redesignated as road number 5, it falls over clay soil. Polygon on polygon. This type of overlay is shown in the next figure, where it is used to answer the queries such as where are the different types of soils or areas lying within urban area, or where is the urban area boundary and where are the clay type of soils within urban area boundaries, or where are the sanded soils within urban areas. The type of queries which can be made may involve a Boolean OR operator type, or it may involve a NOT, and the operation is referred to as a cookie cutting, and it may involve a AND operator. In mathematical terms, these operators respectively refer to as union, identity and intersection. So, in this particular slide what we find is that we have a soil polygon map and we have a urban polygon map, and depending on the type of operation that we would like to have, we would get the result. So, the first case it is a union, wherein it just we are overlaying one map over the other, and thus what happens is it is now splitting the soil polygon map into two regions, one is urban and non-urban, and within the urban area the soil map is splitting the urban area into those areas which have sandy soil and those areas which have clay type of soil. Okay. Similarly, when we go for a erase type of operation, so what it does is that outside the, if I am only interested within the urban area, what is the distribution of soil and not in the non urban area, then the extra portion of the soil boundary in the soil map is erased, because we are only interested within a particular polygon to depict the variation. We can use the AND operator, that is intersect. So, in this particular case we are going to now have a polygon which will have, it will only be just a cutout in the form of as if somebody has taken a bite of a biscuit, and it would be more or less in a sort of a crescent shape in this particular example. So, what we are finding, our result that we are interested is identify urban area on the sandy soil. We are not interested in any other type of soil. So, the net result is only that portion which satisfy the condition, that is urban and sand both are present, highlight that particular portion. So, the same is shown in this particular case. The next type of map overlay is raster overlay. In a raster based system, cell input data represent the raster data structures. A single cell represents a point, a string of cells represent a line, and a group of cells represent an area. Raster overlays employ mathematical operations such as addition, subtraction, multiplication or division on the individual cell values of the input layer to produce an output data. This requires appropriate coding of features represented by points, lines and areas in the input data layer. For example, wells are represented as 1 in the well layer map, while sewer lines are expressed as 2 in the sewer line map. In the land use map layer, the coding may be 3 for wheat, 4 for forest, 5 for clay soil and 6 for urban, while all the cells having features of no interest may be stored as 0 in the data layer. If the codes assigned to different land uses in different layers are same, the interpretation of the results become different. What we are now going to perform on a raster overlay is a operation which is equivalent to vector overlay point in polygon. Since well is a point and the wheat area where there is crop being grown, this is a polygon. What we would like to find out is identify the well which is within wheat areas and identify the well which does not fall in the wheat area. So, what we do is we take two raster maps, undertake the task of subtraction of addition, and this yields a value, that is in the output map all those points where wheat and well both exist, this will now have a value of 4. Areas having only wheat, they will have value of 3, well is equal to 1, and where there is none, then it would be 0. So, based on this, what we find is that the cell which has a value of 4, that indicates a well within the wheat area, whereas the value 1 in the output map, it shows this is a well outside the wheat area. Similarly, we can perform vector inline polygon overlay, that is, I can take a sewer line map and take a urban map and superimpose. Here the sewer line map has a value equal to 2 and urban has been provided a value of 6. So, wherever sewer line is in an urban area, it will have the cell will have a value of 2. Wherever the sewer line is not on urban area, it is going to have a value of 2. Urban areas with no sewer lines, this will have a value of 6, and where there is neither urban or sewer line, it will have a value of 0. So, what we find is that those cells which represent sewer line and fall within urban area, they will have a value of 8. So, we can see there are 2 cells which are having value of 8, that means these indicate that sewer line is passing through the urban areas, whereas value of 6 means it is urban area with no sewer line, or value of 2 means sewer line not falling within urban areas, and 0 means there is neither urban nor sewer line. The third operation, similar to vector operation that we have carried out, that is polygon and on polygon. So, what we can do is we can take a soil map and we can take a forest map. In the soil map, we may identify information regarding the clay type of soil and other type of cells where value of 0, there it is a feature of no interest. Similarly, wherever there is forest, it has been designated, the cells have been designated a value of 4, whereas non-forested areas have a value of 0. So, when I undertake the process of overlaying, the net result is that forest on clay will now have a value of 9, while forest not on clay soil, this would be 4. Clay soil not in forest, it will have a value of 5, and neither it would be 0. So, when we look at the output result, we find there are 3 cells which have the condition of forest on clay soil, whereas all others are different type of conditions which are there. As we have seen in the previous examples, we were dealing with informations which were unique in nature, that is, a single type of information was being carried out. However, larger cell values were being assigned. This operation can be made a little more simpler, wherein objects of interest can be provided a value of 1 and the rest cells are provided a value of 0. So, this would now result into a very unique form of data representation, that is, wherever the union or the presence of both the information is there, the value would be 2, whereas in all other cases it would be less than 2. So, we can very simply make a deduction of the desired area. A further simplification could be that instead of undertaking a multiplication addition operation, we can undertake a multiplication operation, and this would still be better, because wherever the cells which contain the desired information, there the value would be 1 and all other would be 0. A image which we call it as a binary image of bit level 1, that is consisting values of 0 and 1, like operating a electric switch having condition 0 and 1. The next type of spatial analysis is spatial autocorrelation. Spatial autocorrelation may be defined as the relationship between values of a single variable that comes from the geographic arrangement of the areas in which these values occur. It measures the similarity of objects within an area, the degree to which a spatial phenomena is correlated to itself in space, the level of interdependence between the variables, the nature and the strength of the interdependence. That is, spatial correlation is an assessment of the correlation of a variable in reference to spatial location of the variable itself. Assess if the values are interrelated, and if so, is there a spatial pattern to the correlation, that is there any spatial correlation. Spatial correlation tools test whether the observed value of a variable at one location is independent of values of the variable at the neighborhood locations. Spatial autocorrelation may be classified as either positive or negative. Positive spatial autocorrelation has similar values appearing together, while negative spatial autocorrelation has dissimilar values appearing in close association. A positive spatial autocorrelation refers to a map pattern where geographic features of a similar value tend to cluster on a map, whereas a negative spatial autocorrelation indicates a map pattern in which the geographic units of similar values scatter throughout the map. When no statistically significant spatial autocorrelation exists, the pattern of spatial distribution is considered random. Describing spatial autocorrelation. The general method of describing autocorrelation in a variable is to compute some index of covariance for a series of lag distances or distance class from each point. The resulting coloregram illustrates autocorrelation at each lag distance. Membership in a given distance class is defined by assigning a weight to each pair of points in the analysis. Typically, this weight is a simple indicator function taking on a value of 0 if within the distance class or else 0. Weights may be defined in other ways, in which case they may take on non-integer values. The spatial pattern of a distribution is defined by the arrangement of individual entities in space and the geographic relationships amongst them. The capability of evaluating spatial patterns is a prerequisite to understanding the complicated spatial processes underlying the distribution of a phenomena. Spatial autocorrelation indicates the extent to which the occurrence of one feature is influenced by similar features in the adjacent area. As such, statistics of spatial autocorrelation provides a useful indicator of spatial patterns. Indicators of spatial autocorrelation. These could be global indicators of spatial association, that is join count statistics, Moron's I and Gary's C index, null and alternate hypothesis, general cross product statistics, normal randomization and permutation approach, and spatial correlograms. Local indicators of spatial associations could be Lisa-Jai and Lisa-Jai star statistics, Lisa statistics, local Moron, inference to Lisa and spatial outliers. The virogram approach to spatial association in a geostatistical perspective could be virogram with semi-virogram, virogram versus correlogram, fitting a virogram model, robust estimates of a virogram, interpretation of a virogram, virogram and spatial sampling. Measuring spatial autocorrelation. There are three common methods of investigating spatial autocorrelation. The statistical coefficients Moron I and Jerry C provide an indication of the type and degree of spatial autocorrelation present in a data set. A graphical representation of spatial autocorrelation can also be created by means of a semi-virogram. To obtain the spatial autocorrelation coefficient of a variable, we have to correlate the values of that variable for pairs of localities. However, not all pairs of localities will be correlated, only those that are considered neighborhoods. Moron's indices and Gerry's ratios, that is Moron's I and Jerry's C, both are extended from spatial autocorrelation coefficients for aerial objects. Both indices allow using a single value to describe the spatial distribution of features. They can be used to determine the degree of adjustment necessary when modeling the phenomena. Moron's I is produced by standardizing the spatial autocovariance by the variance of the data using a measure of connectivity of data. Jerry C uses the sum of squared differences between the pairs of data values as it is a measure of covariation. Jerry C index. This statistics was developed by Roy C. Jerry. The computations of Jerry C results in a value within the range of 0 to +2, with 0 being a strong positive spatial autocorrelation through to 2, which represents a strong negative spatial autocorrelation. Jerry C can be defined as n minus 1 double summation of W I j multiplied by the square of the difference of x I minus x j divided by 2 W divided by this multiplied by the summation of x I minus x bar whole square, where n is the number of observations, W I j is the distance or the spatial lag between pixels I and j, x I is the dn value at the location I and x j is the dn value at location j. Moron's I. Measuring the correlation, that is simultaneous change in values of two numerically valued random variable among the neighborhood observation in the pattern is done using spatial autocorrelation statistics Moron I. Moron's I is defined as a measure of the correlation amongst neighboring observations in a pattern. The computations of Moron I is achieved by the division of the spatial covariation by the total variation. The general formula of computing Moron's I is n over double summation of W I j multiplied by the double summation of W I j multiplied by x minus x bar multiplied by x j minus x bar divided by summation of I to n x I minus x bar whole square, where n is the number of spatial units indexed by I and j, x is the variable of interest, x bar is the mean of x and W I j is the matrix of spatial weights. The resultant values are in the range from -1 to 1. Positive signage represents positive spatial autocorrelation, while the converse is true for negative signage, with a 0 result representing no spatial autocorrelation. It has been found that the moron's eye is inversely related to Jerry C, but it is not identical. Moron's eye is a measure of global spatial autocorrelation, while Jerry C is more sensitive to local spatial autocorrelation. Then we come to the next type of analysis procedure, which is the network analysis. In the context of GIS, a network is defined as a set of interconnected linear features through which resources can flow. Common examples of network include highways, railways, city streets, canals, rivers, transportation routes such as for garbage collection, mail delivery, school buses and utility systems, for example, telephone, electricity, water supply and sewage. There are many spatial problems that require the use of network analysis for their solution. Use of network analysis. To find the shortest path in terms of physical distance or least cost that can be followed to visit a series of features in a network known as path finding. To assign one or more positions of a network to be served by a facility or business location called as allocation. To find all portions of the network that are connected with the movement of a particular feature, that is cities transport, called as tracing. To depict the accessibility of a location and the interaction that occur between different locations based on a technique known as gravity model. This is widely used in economics, geography, engineering and urban planning, known as spatial interaction. To generate a distance matrix between different pairs of location in the network, known as distance matrix calculation, and to determine simultaneously the location of existing and planned facilities as well as the allocation of demands of these facilities, known as location allocation model. So, let us look at some of the typical network problems which can be solved using GIS. First is the shortest path problem. The shortest path, which is the shortest distance or the least time path between 2 points in a on a network, is defined by proximity analysis in a GIS, raster GIS. Impediments to a travel are added to a raster grid by increasing the value of the cells that are barriers to travel. Then the result is obtained as least cost route. Vector GIS network analysis of finding shortest path is more flexible and provides a thorough impediment analysis such as restrictions and congestions in traffic routes. Route tracing. Route tracing through network analysis is required to identify the resources with special reference to stream networks and services such as sewage system and cable TV networks. Other applications are determination of streams contributing to a reservoir, customers serviced by a particular sewer main, or clients affected by a broken cable. The key concept in route tracing is the connectivity of network links at network nodes. Knowledge of direction of flow is an important factor for route tracing. Therefore, each link in the network must be associated with a direction of flow that can be defined at the time of digitization process by keeping the directions of the digitization and flow same. Now, tracing the links downstream or upstreams of a point on the network is performed by moving in the direction of flow or against it. Another problem is the salesman travel problem. A salesman may be required to visit a specific set of clients in a day for which he would like to know the best, usually the quickest route that he can follow to finish his job. Similar problems are collection of garbage and distribution of malls. Such problems are solved by analyzing the orders of stop and paths between them. Getting solutions of such problems is a complex task, and to simplify such tasks, the ordering of the stops can be determined by calculating the minimum path between each stop and every other stop in the list based on the impedance met in the network. A trial and error method, also referred to as heuristic, is then applied to order the visits, minimizing the total impedance from first stop to the last one. An important application of network analysis is allocation of resources. This is done by modeling the supply and demand, in which help of movement of goods, people and information or services through the network are required to match the demand with the supply. Allocation of resources is usually done by allocating links in the network to the nearest center of supply, taking into account impedance values. The maximum catchment area for a particular supply center can also be determined on the basis of the demand located along adjacent links in the network. A situation may arise by imposing limitations on the supply and demand, in which some parts of the network may not be serviced despite a demand being present in that part. Such problems can be resolved by reducing the supply to some part of the network or by identifying the optimum location of a new center to meet the shortfall in supply relative to demand. Another very important aspect in spatial analysis is digital terrain visualization. Visualization of DTM in the context of GIS has two primary objectives. First, to communicate geographic information and to provide a means of data exploration and hypothesis refinement, and therefore, it is an integral component of DTM. Visualization means representing relevant terrain information about a given geographic area that results from the analysis of the characteristics of that geography and related spatial phenomena. There are numerous well developed techniques and some are being developed. These techniques have been classified according to the dimension of the graphical display and have been represented below. Two-dimensional visualizations of terrain. The most conventional and commonly used method of digital terrain visualization is using contours. This method is a quantitative approach of representing 3D terrain in two dimensions. A major drawback in this approach is that an inexperienced map user finds it difficult to visualize terrain in 3-dimensional terrain from 2-dimensional representation. As a result, different methods have been developed to create a 3-dimensional impression of relief using contours. Methods of representing the 3-dimensional information is through analytical or automated shading methods. Hill shading methods of 2-dimensional terrain visualization is based on the principle of applying illumination to the surface normal vector for the DM or tin as shown here. So, in this case, a light vector has been projected onto the ground surface, and based on the orientation of the ground features, different shadows or shades are being provided, and this helps in the creation of the third dimension. Similar principles, but different in algorithm, is applied in hill shading using DM. Hill shading is referred to as a qualitative method of 2-dimensional terrain visualization, and therefore, numerical values of elevations cannot be measured from the display. 2.5 dimensional visualization of terrain. It is possible to simulate 3-dimensional terrain from a 2-dimensional display through the use of clever graphics. However, technically a 2.5 dimensional display is basically an isometric model. In an isometric model, the principal axis x, y and z are equally inclined to each other and the scale along these axes are also same. Therefore, 2.5 dimensional visualization, though being relatively easy to implement from programming point of view, it does not create the impression of visual depth. Classical uses of 2.5 dimension approaches are frame wire diagram. So, this particular slide shows a 2.5 dimensional visualization of the terrain, wherein the twisted form of the wires help in the viewer to visualize the change in the curvature or the slope of the ground. A more realistic perspective of the terrain is created by draping other kinds of images on the 2.5 dimensional model. However, with the development of powerful computer graphics softwares and hardware, 3D dimensional terrain visualization has become possible, superseding the 2.5 dimensional visualization. So, here in this particular figure, we find that over the wire diagram another information has been overlaid. This can be an aerial photograph or it could be a satellite data. With this, I have now discussed all the method of modern techniques of surveying. In my next session, I would discuss some of the applications to highlight the utilities of these techniques. Thank you.